The Type 212CD attack submarine represents something very different in the world of underwater warfare. Short for Common Design, the Type 212CD is a joint program between Germany and Norway, led by the German shipbuilder Thyssenkrupp Marine Systems. It builds upon the success of the smaller German-Italian Type 212A class, but introduces a complete redesign. The project originated as a joint development between the German Navy and the Royal Norwegian Navy. Norway has committed to building 6 boats, while Germany plans to build 6 and may order 3 more, bringing the total for the German Navy to 9 boats. In July 2026, Canada selected the Type 212CD design for its Canadian Patrol Submarine Project to replace its aging fleet of 4 Victoria-class submarines. Canada plans to acquire up to 12 new submarines. This decision brings Canada into a trilateral defense and industrial framework alongside Germany and Norway, creating one of the largest conventional submarine programs in NATO history. Understanding the importance of the Type 212CD requires an understanding of how sonar systems find conventional submarines. Passive sonars relies on hydrophones to detect noise generated by a target, such as propeller cavitation, diesel engines, cooling pumps, or internal machinery. Passive sonars do not emit any acoustic energy of its own, including the classic ping. Diesel-electric submarines excel at evading passive sonar. When running on battery power, the electric motors generate negligible vibration and are very quiet. With the addition of Air-Independent Propulsion, or AIP, these vessels can remain submerged for weeks without running a diesel engine to recharge. Against passive sonars, a conventional submarine operating at low speed beneath the surface is very difficult to find. Passive sonar struggles to isolate the acoustic signature from the background noise of the ocean. Consequently, modern anti-submarine warfare forces rely heavily on active sonar. Surface ships like the Type 052D destroyers of the Chinese Navy deploy powerful variable-depth active sonars. Maritime patrol aircraft like the Boeing P-8A Poseidon drop active sonobuoys, while naval helicopters lower active dipping sonars into the water column. Active sonar emits a sound that travels through the water, stops at a submarine's hull, and bounces back to a receiver. Traditional cylindrical submarines present a rounded, perpendicular target surface to an incoming sonar pulse from almost any angle. This returns a strong acoustic reflection straight back to the emitting sonar. A submarine could be completely silent, yet remain fully visible to active sonar pings. Historically, submarines defended against active sonars using anechoic tiles. These synthetic rubber or polymer tiles are glued to the outer hull. They contain tiny voids designed to absorb incoming acoustic energy. While effective against higher sonar frequencies, anechoic tiles have limitations. They can degrade over time, peel off during prolonged deployment, and offer reduced effectiveness against lower frequency, long wavelength active sonar. The Type 212CD moves beyond reliance on anechoic tiles alone. It has a far more comprehensive answer to active sonars. It combines anechoic tiles with active stealth shaping for the outer hull. Departing from the smooth, cylindrical shapes traditional to submarine architecture, the vessel uses a diamond-shaped, faceted outer hull. This angular approach mirrors the radar cross-section reduction techniques used on stealth aircraft, like the F-35 fighters or the B-2 Spirit. By applying angular geometry to underwater hulls, the Type 212CD fundamentally improves how submarines defend against active sonar. When an active sonar wave hits these inclined surfaces, the acoustic energy reflects away at oblique angles, instead of returning directly to the enemy ship or helicopter sonar. The pain is bounced off into the surrounding ocean or absorbed into the seabed. This drastically reduces the signature strength of the vessel, making the submarine appear much smaller on active sonar displays, or causing the sonar return to fall below the detection threshold entirely. This acoustic stealth concept is not entirely exclusive to Germany and Norway. The Chinese PLA Navy introduced a similar angular design on its Type 039C class submarine. The Type 039C features a distinctive angled sail structure designed to reduce active sonar reflection. The Type 212CD applies this angular geometry across the entire length of the outer hull, forming a complete stealthy enclosure over the pressure hull. The outer diamond hull of the Type 212CD creates a double hull arrangement over much of the vessel. The outer shell is non-magnetic and hydrodynamic to an extent, while the heavy inner pressure hull houses the crew, combat systems, and machinery. One of the most consequential design changes in the Type 212CD is its massive increase in displacement. The older Type 212A submerged displacements sit at roughly 1,800 tons. The Type 212CD expands to approximately 2,800 tons submerged, representing a displacement increase of more than 50%. The overall length grows from 56 meters to approximately 74 meters, with a beam expanding from 7 meters to over 10 meters. While the displacement increase in part reflects the change from a single hull design onto a double hull design, it also reflects a substantial increase in internal volume. This volume growth directly improves the submarine's passive stealth. Inside any submarine, machinery vibration transferred through the hull into the water is the primary source of passive acoustic emission. To prevent this, navies mount critical machinery on shock-absorbing elastic mounts known as raft. On smaller submarines, internal space inside the pressure hull is restricted. Designers must mount equipment closer to the hull framing, limiting the size of acoustic isolation raft. The extra internal volume of the Type 212CD allows for larger multi-stage floating raft systems. Diesel generators, hydraulic pumps, air conditioning units, and electric motors are mounted on heavy structural frames suspended by elastic isolators. These rafts sit inside a secondary isolated cradle before connecting to the pressure hull. By double isolation of mechanical vibration, the physical movement of operating machinery is dampened before reaching the pressure hull. Combined with the water gap between the inner pressure hull and the outer diamond shell, passive noise emissions are suppressed to unprecedentedly low levels. The increased internal volume converts the operational footprint into a near-silent acoustic background. The extra volume also transforms the operational role of the submarine. The original Type 212A was designed primarily for coastal operations in the Baltic Sea and the North Sea. Its compact size allowed it to operate in shallow waters, but limited its endurance, range, weapon loadout, and payload capacity. The Type 212CD is built as an ocean-going, blue-water attack submarine. The larger hull provides expanded tanks for fuel and fresh water, more space for crew provisions, and increased ammunition storage. It allows the Type 212CD to deploy far from home ports, perform extended patrols in open ocean environments like the North Atlantic, and conduct prolonged missions under Arctic ice. The Type 212CD retains the hydrogen fuel cell air-independent propulsion system pioneered on the Type 212A, but incorporates upgraded fuel cell modules. Fuel cell AIP combines stored liquid oxygen and hydrogen to generate electrical power silently without combustion. The only byproduct is pure water. Unlike closed-cycle Stirling engines, fuel cell AIP has no moving parts, making its operation completely silent. The upgraded fuel cell system on the Type 212CD delivers higher power output and greater efficiency, allowing the submarine to remain fully submerged for weeks at low cruising speeds without ever needing to snorkel. The predecessor, Type 212A, relied on conventional lead-acid battery tanks to power the main electric motor during high-speed maneuvers. The Type 212CD incorporates lithium-ion batteries. Lithium-ion batteries offer several distinct advantages over lead-acid cells in submarine applications. They provide much higher energy density, storing more electrical power within the same physical footprint and weight allowance. They support much faster recharge rates, drastically reducing the time the submarine must spend running its diesel engines at snorkel depth to recharge the battery banks. The combination of advanced fuel cell AIP and high-capacity lithium-ion batteries gives the Type 212CD a very capable energy architecture. Fuel cells handle long-duration, low-speed stealth cruising, while the lithium-ion batteries supply rapid power for high-speed transit and combat engagements. The Type 212CD has 6 standard 533mm torpedo tubes. These tubes launch modern heavyweight torpedoes, anti-ship missiles, and naval mines. However, the submarine is also designed to deploy novel defensive weapons directly from its tubes. These weapons are still in development, so information and confirmation remain limited. One of these integration options is an anti-torpedo torpedo, such as the Sea Spider developed by Atlas Electronic. Historically, when an enemy ship, submarine, or aircraft launch a homing torpedo at a submarine, the target's vessel could only deploy soft-kill countermeasures. These included acoustic decoys, jammers, or bubble curtains to try to confuse the torpedo's sonar guidance. Modern torpedoes feature intelligent digital processing that can distinguish between acoustic decoys and actual submarines, making soft-kill countermeasures increasingly unreliable. An anti-torpedo torpedo provides a hard-kill defense. Upon detecting an incoming enemy torpedo via the submarine sonar, the Type 212CD can launch a small, high-speed interceptor torpedo. The Sea Spider uses its own active acoustic seeker to track the incoming torpedo and detonates an explosive charge in close proximity. This destroys the attacking weapon before it reaches the submarine. Hard-kill torpedo defense fundamentally alters underwater tactical engagements, giving submarines an active intercept capability. Another specialized capability planned for integration into the Type 212CD is a fiber optic guided anti-air missile fired from the submarine's torpedo tubes while fully submerged. Submarines have traditionally been defenseless against anti-submarine warfare helicopters and maritime patrol aircraft. If a helicopter drops a dipping sonar nearby, a submarine has no option but to attempt evasion. Submarine-launched anti-air missiles change this dynamic by allowing the submarine to engage airborne threats from below the surface. Deploying an anti-air missile from a submerged submarine presents severe challenges. Tactical radar signals cannot penetrate seawater, meaning the submarine cannot use conventional radar to lock onto aircraft prior to launch. Water also introduces extreme density transitions as the missile exits the torpedo tube, travels through the water column, breaks the sea surface, and ignites its flight motor. The Type 212CD's intended anti-air missile, the IDAS, tries to solve these problems using a high-tensile fiber optic cable that extends from the submarine during launch. The missile breaks the surface using a solid fuel rocket motor and transitions to aerial flight. An infrared seeker on the missile head transmits real-time video back to the combat system inside the submarine's command center via fiber optic link. The operator can manually lock onto an anti-submarine helicopter, corrects the missile's trajectory mid-flight, or aborts the strike if a target is misidentified. Alternatively, initial target's coordinates can be fed to the missile using data gathered from the submarine's optronic mast. The nervous system managing these weapons and sensors on the Type 212CD is the ORCA combat system, developed by KTA Naval Systems, a joint venture between Kongsberg and Thyssenkrupp. ORCA integrates sonar data, radar, optronics, electronic support measures, and tactical data links into a unified command interface. It uses an open computing architecture that allows software upgrades and artificial intelligence to be integrated over the operational lifespan of the submarine. The selection of the Type 212CD by Canada in July 2026 under the Canadian Patrol Submarine Project highlights the platform's export appeal and strategic relevance. Canada used a competitive procurement process evaluating multiple international designs. The primary competitor was South Korea's KSS-3 Batch 2 submarine. The KSS-3 is a highly capable 4,000-ton design equipped with a vertical launching system for submarine-launched ballistic and cruise missiles. However, several strategic and operational factors led the Royal Canadian Navy to favor the German Type 212CD. A central factor was NATO interoperability and alliance cohesion. By selecting the Type 212CD, Canada joins Germany and Norway in a standardized submarine framework. This commonality enables shared logistics networks, joint maintenance, common crew training, and pooled spare parts inventories across the North Atlantic Alliance. For a navy operating across vast oceans, shared NATO infrastructure reduces long-term life cycle cost and improves availability. Environmental suitability played a critical role in the Canadian evaluation. Canada possesses the longest coastline in the world, spanning the North Atlantic, the North Pacific, and the Arctic Oceans. Operating in the Arctic requires a submarine capable of negotiating ice-covered oceans, which the Type 212CD is better suited to do. The shift toward stealthy geometries and hull form in submarine design reflects a broader evolution in undersea warfare. As sensor technology advances, relying on a single stealth technique is no longer sufficient. Passive acoustic quietness remains vital, but active sonar evasion, magnetic signature suppression, infrared management, and soft kill and hard kill weapons integration must operate in unison. The Type 212CD considers all of these factors in its design. The ability to scatter active sonar pulses, remain silent to passive listening, and deploy hard kill weapons makes the Type 212CD one of the most survivable conventional submarines in modern naval history. Like the South Korean KSS-3, the Type 212CD demonstrates that diesel-electric attack submarines are no longer confined to coastal defense roles. By merging large hull volumes with advanced lithium-ion batteries and fuel cell air-independent propulsion, the Type 212CD sets a new benchmark for blue water capabilities for non-nuclear submarines. If you want to learn more about the KSS-3, the Dosan and Chanho class of South Korea, another highly capable conventional submarine by modern standards, please watch this video right here. See you next time.